Imagine a limit. Walls can be torn down. Rules can be changed. Records can be broken. The history of humanity is the story of how everything once deemed impossible eventually became possible. But there are certain limits set by the universe, and they are different. The speed of light is one of them. It's approximately 300,000 kilometers per second. In 1 second, it can circle the Earth 7.5 times. It reaches the moon in 1.3 seconds. It reaches the sun in 8 minutes. And nothing, no matter matter, no object, no information, can exceed this speed. This is not a theory. It is one of the most fundamental laws of the universe. So why is that? And if we could reach it, if we could actually bring our speed up to that exact point, what would happen? Today, we'll explore this question step by step, using Einstein's own answers. But let's say this right from the start. The answer is much stranger than you might expect.
In 1895, a 16-year-old boy asked himself an intriguing question. If I were to run alongside a beam of light at the same speed as it, what would I see? That boy was Albert Einstein, and this question occupied his mind for 10 years. In everyday life, logic tells us this. If a car is traveling at 100 kilometers per second, and you're also traveling at 100 kilometers per second, the car appears to be standing still relative to you. That's relativity. Speed depends on the observer. But what about light? If you ran at the same speed as light, light should come to a stop relative to you. You should have seen a frozen electromagnetic wave. But Maxwell's equations prohibited this. Electromagnetic waves could not come to a complete stop. The laws of physics wouldn't allow it. So there was a contradiction. Either Maxwell was wrong, or the relativity of speed didn't apply to everything. Einstein thought about it for 10 years, and in 1905, he found the answer. Both were true, but we had to rethink everything about space and time.
Einstein's theory of special relativity is based on two fundamental principles. First, the laws of physics are the same for every observer moving at a constant speed. Second, the speed of light is constant for all observers, regardless of the speed of the source or the observer. This second principle changed everything. If the speed of light is the same for everyone, whether for an astronaut inside an accelerating rocket or for someone standing still on Earth, then space and time themselves must change. How? As you accelerate, time slows down. This is called time dilation. As you accelerate, length shrinks. This is called length contraction. As you accelerate, mass increases. This is called relativistic mass increase. These three effects become increasingly pronounced as you approach the speed of light. And when you reach the exact speed of light, mathematically speaking, time comes to a complete standstill. Length shrinks to zero, and mass goes to infinity. Infinite mass. That requires infinite energy. And there is no infinite energy in our universe. That is why reaching the speed of light is impossible. It's not a ban, it's a mathematical barrier. So, does this barrier exist only in theory?
No. We feel this barrier every day. Think of GPS satellites. GPS satellites fly about 20,000 kilometers above Earth at a speed of 14,000 kilometers per hour. This speed is a very small fraction of the speed of light, about 0.004%. A small effect, but it's there. According to Einstein's equations, because of this speed, the satellite's clocks run about 7 microseconds slow each day. At the same time, because they are far from Earth's gravity, due to the effect of general relativity, they run 45 microseconds fast each day. The net difference? About 38 microseconds per day. It seems small, but if the GPS system didn't make this correction, an error of about 10 kilometers would accumulate every day. The map on your phone would lead you astray. The theory of relativity is at work in the phone in your pocket. But what if we take it to the extreme? What if we actually approached the speed of light.
In this section, where the experiment is all about the mind, let's put you in a rocket. Your initial speed is 0. You fire up the engine. You've reached 10% of the speed of light, 30,000 kilometers per second. Clocks outside are ticking slightly differently, but you can't feel the difference. 50% of the speed of light, 150,000 kilometers per second. Time dilation is becoming noticeable. While 1 hour passes outside, about 52 minutes pass for you. 90% of the speed of light. Time dilation is becoming dramatic. While 1 hour passes outside, only 26 minutes pass for you. And everything in the rocket's direction, distances, objects, is compressed and shortened. 99% of the speed of light. While 1 hour passes outside, only 8.5 minutes pass for you. And the rocket's mass is now 7 times what it was at the start. It requires 7 times more fuel to maintain the same acceleration.
99.9%. 1 hour outside equals 2.7 minutes for you. 99.9999%. 1 year outside equals just a few minutes for you. And with every step, the energy required for the next step increases exponentially. The energy required to reach exactly 100%, the speed of light, is infinite. Not even the total energy of the universe would be enough. But what about photons? Light particles travel at the speed of light. Why isn't this a problem for them?
Because photons have no mass. This sentence seems simple, but it contains a revolution. In Einstein's equations, the energy required to reach the speed of light is directly proportional to mass. The greater the mass, the greater the energy required. If mass is 0, the energy required is also 0. Photons move at the speed of light from the moment they come into existence. They don't accelerate. They start out that way. And that is precisely why matter cannot reach the speed of light. Because matter has mass, and anything with mass requires infinite energy to reach the speed of light. This is a fundamental asymmetry of the universe. The speed of light belongs to the world of massless particles. Matter cannot enter that realm. What about exceeding the speed of light? Is it completely forbidden?
Here's an interesting question. Einstein's theory states that an object with mass cannot reach the speed of light, because what starts below it cannot go above it. But what about something that starts just above the speed of light? Theoretical physicists have considered this, and they proposed hypothetical particles they called tachyons. Tachyons are particles that always move faster than the speed of light. When they slow down, they approach the speed of light, but they can never fall below it. The problem is this: there is no observational evidence for the existence of tachyons, and theoretically, they pose serious problems. In particular, they violate the principle of causality, that is, the rule that cause precedes effect. What about warping space itself? The idea of a warp drive isn't actually pure science fiction. In 1994, physicist Miguel Alcubierre proposed a mathematically consistent model of a warp drive. The idea is this: if you warp space-time, you can compress the space in front of the rocket and expand the space behind it. The rocket isn't moving, space itself is moving. This doesn't violate the speed of light limit, because matter isn't moving, space is moving. But there's a problem. To make this model work, you need negative energy, and we still don't know if negative energy exists. It's theoretically possible. Practically, at least for now, it's unattainable. Now we come to the strangest part. Let's say that one day humanity becomes capable of traveling at a speed very close to the speed of light. Let's say 99.9999% of the speed of light. You're heading to Alpha Centauri. It's 4.37 light-years away. To someone watching from Earth, this journey would take about 4.37 years. Since you're traveling at nearly the speed of light, it takes almost as long as light itself. But what about you? Due to time dilation, this journey might last only a few days for you, or a few hours. It depends on your speed. When you return, years may have passed on Earth,
but you've hardly aged at all. This is called the twin paradox. Theoretically, someone traveling at speeds close to the speed of light ages much more slowly than their twin left behind. It's not actually a paradox. It's mathematically consistent. But because it contradicts our intuition, it's been labeled a paradox. And the most surprising part? This effect has already been measured. The lifetimes of particles moving at high speeds are extended. Atomic clocks carried on airplanes run slightly differently from those on the ground. Time dilation is real. And as you approach the speed of light, this effect becomes dramatic.
We said that reaching the speed of light requires infinite energy. But that's not the real message of this story. The real message is this: the universe has set a limit for you. And to discover that limit, a genius emerged. A 16-year-old who dreamed of running alongside the light. And that dream gave birth to one of the greatest revolutions in physics. From GPS satellites to particle accelerators, from atomic bombs to solar energy, the echoes of Einstein's question are everywhere today. We say that limits are obstacles to discovery, but sometimes a limit is the beginning of understanding. We cannot reach the speed of light, but by understanding it, we've unraveled the structure of the universe. We learned that space is curved, that time is relative, and that energy is related to mass. Perhaps the greatest discoveries are made at the edge of the impossible. So, do you think humanity will one day be able to travel at speeds close to the speed of light? And if we could, where would you want to go? Let's discuss it in the comments.